Hello there, Mr. Sutton here, bringing you the Algebra 2 1-1 Part 2 homework solutions. In general, we're dealing with parent functions and transformations. Specifically on this one, we're going to be focusing on dilations and reflections. For this problem, we're trying to graph and describe the transformation for g of x equals negative x. Well, this is just f of x equals x for the parent function. It's just a line with the points 0, 0, and 1, 1 still. Now for the transformation, we can think of this as being outside the function. It actually won't matter whether it's inside or outside, but I like to think of all the linear stuff as happening outside of x. So this is going to be a negative outside, which means we have a vertical reflection, or a reflection over the x-axis, as it were. So that means that if I think about this vertically, my x's can stay the same, but for the y's, I'm going to have to do negative y. So we still have the same x's, 0 and 1. And for the y's now, negating these, we still have 0, but now this is going to be negative 1. So graphing those out, we have 0, 1, or 0, 0 rather, and 1, negative 1 down here. And then there's our reflected line. On this problem, we're trying to graph this function and also describe the transformation going on. Since this is a linear function, we have an x right here. I'm going to use y equals x and its parent table to help me graph this out. So I'm just going to use the points 0, 0, and 1, 1. There's lots of other points, but we really only need 2 for a line. So now what's actually going on here in terms of transformations? Well, all transformations with lines can be thought of as vertical. There's no really inside versus outside for these. So this 3 next to the x is, because it's multiplying here, this is giving us a vertical stretch, and this plus 2 is giving us a translation of up 2. So implementing that in a new table for f of x now, x is just going to stay the way it is. We don't need to change the x with a linear function transformation. For the y, though, we're multiplying the y value by 3. That's what this times 3 is giving us. And we're also adding 2 after we do that. So I'm going to write 3y plus 2 in terms of how I'm changing all my y values. The x's are pretty easy. It's just what we started with, 0 and 1. For the y values now, we've got 3 times 0 plus 2, which is 2. And then 3 times 1 plus 2, which is, let's see, that's going to be 5. And now I can just plot these and graph it out. So we have 0, comma 2, which is right there. And then 1, comma 5 is going to be up here. And then we can graph that. Just connect the dots with a line. Now, if you think about this, kind of the old way of thinking about it with y equals mx plus b and slope-intercept and all that, we have a y-intercept of 2. We have a slope of 3, so we're going up 3 over 1, and that also gets us the same picture. On this problem, they're asking us to transform this function and describe what we did. So this is a linear function. We have the x to the first power going on. You might recognize this as being in y equals mx plus b form. So I'm going to use y equals x as kind of my parent function. And the table that goes with that, we have the points 0, 0, and 1, 1, and many other points, but we just need 2. So what's happening now to this y equals x as a result of these transformations? Well, this negative out here is giving us a vertical reflection, and this plus 5 is going to be giving us a shift up, a translation up of 5. Now, there's another way you could think about this. If you think of this as like an inside sort of deal, this could be thought of as a horizontal reflection, but they look the same with a line. And if we factored a negative out, we would have negative and then x minus 5 inside, and we'd be shifting everything right 5, which would still end up giving us the same picture. So let's go ahead and make a new table with these values here, and I'll call that h actually. There we go. Don't want to confuse people. And now for the new x and y's, the x's can stay the same. Again, with lines, I just do everything as a vertical transformation. And then for the y values, we are negating the y values with this reflection, and translating up by 5 means after we do this negation, we have to add 5. So negative y plus 5 gives us a new rule for that. So for the x's, I still have 0 and 1. For the y values, negative 0 plus 5 is 5, and negative 1 plus 5 gives us 4. So we've got 0 comma 5 up here, 1 comma 4 is right there, and there's your line going through those 2 points. And if you think about it as y equals mx plus b, slope is going to be negative 1, so down 1 over 1, and there's our y-intercept of 5. For this problem, we're going to figure out the transformation and graph this function. This is absolute value for the parent function, so here's my absolute value parent table where we have negative 1, 1, 0, 0, and 1, 1. And then for the transformations, this negative 3 out here is giving us a vertical reflection and stretch since it's outside the function. And this negative 1, since it's also outside the absolute value, that's an up-down shift. It's specifically a shift of down 1. So vertical reflection stretch and translate down 1. So let me come up with a table for h of x now with some new rules. X is just still going to be x. There's nothing that actually happened to the x's here. Nothing happened inside the function. For the y's, though, we have to do negative 3 times y and then minus 1. So that's going to give us, for the x's, still negative 1, 0, and 1. For the y's, we've got negative 3 times 1 is negative 3. Minus 1 from that, we've got negative 4. Then we've got negative 3 times 0 is 0. Minus 1 is negative 1. And then we still have 1 becoming negative 4 when we use that rule. All right, so putting all this on a graph, we have negative 1, negative 4 right there. 0, negative 1 is there, and we have 1 comma negative 4 down here. And let's do a little v through those. So just double checking our transformation. We've got our vertical reflection. We've got our stretch here. It's taller than it used to be. And then we've translated everything down after all of that by 1. For this problem, we're going to graph the function and figure out the transformation going on. So we've got the absolute value function. Let me set up a table for that. We've got negative 1, 1, 0, 0, and 1, 1 for my 3 points I always like to use for this. For the transformations, this times 2 inside is giving us a horizontal, let's see, it's going to be a shrink because it's counterintuitive, right? We're actually dividing all the x values by 2. And then this plus 3 outside is giving us a translation of up 3. So we've got our new rule now for x in the f of x table here. We're going to be doing 1/2 times all the x values. It's inverse of what it looks like if it's inside the function. So 1/2 x. For the y's, we're just adding 3 to those, shifting up by 3. So for the new x values, we just have 1/2 times all these originals. So this is now going to be negative 1/2, 0 is still 0, and positive 1/2. For the y's, we just add 3 to all these. So this becomes a 4, a 3, and then a 4. Putting those all on our graph, we have negative 1/2, 4, which is right about here. 0, 3 is here, and 1/2, comma 4 is back up here. So let's draw the v through those. And let's just check our transformations. It looks like we did shrink horizontally. We're closer to the y-axis, and everything got shifted up 3. For this next problem, which is on the honors problem set only, we're trying to graph the g function and describe the transformation. So let's start with our parent table, absolute value. I like to start there, negative 1, 1, 0, 0, and 1, 1. And then for the transformations, the negative outside the absolute value is giving us a vertical reflection. And then we've got some shifting going on. The minus 1 inside shifts us to the right by 1. The minus 1/2 outside shifts us down by 1/2. So writing all that out, vertical reflection and a translation right 1 and down 1/2. So let's come up with our new table now with our new rules for x and y. And that should actually say g. There we go. So this is the g table we're creating here. For the x's, the only thing happening horizontally is we're shifting right 1. So I'll write x plus 1 to make that happen. Vertically, we are reflecting, so we have to do a negative y, and then we have to subtract 1/2 from whatever that becomes. So for the x's, just adding 1, Negative 1 and 1 is 0. 1 plus 1, or 0 plus 1 is 1. 1 plus 1 is 2, so nothing earth-shattering going on over there. The y's are going to be a little trickier, so we have negative 1 minus 1 half. That's going to be negative 3 halves or negative 1.5, however you want to express that. And then we have negative 0 is still 0 minus 1 half. And then 1 becomes negative 3 halves again. Putting this on a graph, we've got, let's see here, 0 minus 3 halves. That's right here between negative 1 and negative 2. Next we have 1 comma negative 1 half. And finally we've got 2 comma negative 3 halves again. And then there's our v. So in terms of what happened, we reflected it vertically, definitely happened. And we also shifted things right 1 and down 1 half. So everything checks out. On this problem, we have a table showing speeds of a car as it travels through an intersection with a stop sign. So we've got, let's see, we're negative 100, and at negative 100 yards away, we're going 40 miles an hour. And then you can see that as we get closer, the speed is approaching 0. And then as we get further away from the stop sign, the speed increases again, which is about what you would expect. So we want to estimate, first off, we want to know what type of function we can use to model this data. And we've, at this point in our learning, got a choice between a constant function, a linear, and an absolute value. Those are kind of the three function families we're going between. And then we want to use that to estimate the speed of the car when it's 20 yards past the intersection. So taking a look at what's happening here, we notice that as we get less negative, we're getting closer to 0, and as we get more and more positive, we're getting further away from 0. But in both cases, you notice that our speed is always positive, even if the input, the displacement, is negative. The fact that we always have a positive speed indicates that this must be an absolute value sort of function. Otherwise, we can't just turn positives into positives or negatives into positives and keep the positives positive. Only absolute value can do both of those things. If it were linear, then you would either be turning, if you were turning negatives into positives, then the positives would turn into negatives. So we've got an absolute value, and what's the specific relationship? If you look here, there's a ratio that keeps happening. So 100 over 40, that reduces to 5 halves. So if you multiply 100 by 2/5, you get 40. 2/5 times 50 will give you 20. 2/5 times 10 gives you 4. And the 2/5 rule seems to work for all of these translations here. Although those wouldn't actually be translations, those would be dilations. So our rule then, speed is going to be 2/5 times the absolute value of displacement, which we can write as s of x equals y equals 2/5 absolute value of x. Now to estimate the speed of the car at 20 yards, we just have to plug in 20 for x. So the absolute value of 20 is just still positive 20, so that's fine. And then 2/5 of 20, well, 20 divided by 5 is going to be 4, times 2 gives us 8. So that's going to be 8, let's see, this is miles per hour for the speed.